So we are going to be doing 8 questions, and this should not take more than an hour. Let's just get started. Okay, so first, for elastic filament, draw an elastic filament. It's found at finite range in temperature. A displacement x requires a force. So they have given us g as a function of x and temperature. Wow, nice. So that's one equation. And then where a, v, c are constants. Furthermore, its heat capacity at constant displacement is proportional to this temperature. So the heat capacity at constant displacement sounds like CV basically. So basically they have given us partial E by partial T at constant volume, and that's given. Fine, whatever, we'll use that later. So what do you want? First question is use an appropriate Maxwell relation to calculate partial S by partial X at constant temperature. Yeah, okay, I get it. Partial S upon partial X at constant temperature. uh, Oh yeah, okay. So this is similar to S sub V at constant temperature, and we have in fact calculated this in the past somewhere. But anyway, so let's just go back to the main equation. Right. So P sub Y. This is the main equation, and I guess at this point it's just better if we sort of derive the Maxwell's relations beforehand, so that you know we don't really have to keep on deriving these things again and again, because I suffered from that the last time. So let's just put x equal. So there's going to be like 4 main Maxwell's equations, right, which are like useful. Yeah. Right. Yeah, okay, let's just get started. So let's just put x equal to p and y equal to t. Let's see what we get. Let's just get p sub. Okay, so v sub y is v sub t at constant pressure. So minus t sub x, which is t sub p at constant y. So wait, that doesn't make sense. That's actually 0. This is equal to p sub y. So p sub t at constant. Well, that's not good because p is x, so this should just be 0. Right. So just equal to minus. So t sub y. Okay, that's 1. So just s sub x is p. So s sub p at constant temperature. All right. So that's one relation. Let's derive another relation. So let's just say x equal to, once again, p, y equal to s. That's going to give us another relation most likely. Right. And so with p you can have t or s, you cannot have v, because with p and v that will give us a big one, and that's not what we want. So let's just put that in and see what we get. So let's just have 1 and then v sub s at constant pressure. That's equal to, so p sub y, that's gonna be gone, and then s sub x, that's gone as well. So this is just equal to t sub x is t sub p, and this is at constant entropy. And yeah, that's the other relation. So 2 done, 2 more to go, and trust me, these are going to come in handy eventually. So now let's just go for x equal to so pressure is more or less done, so just go for volume, and y equal to entropy. Yeah, right. Just do that. What do you get? So p sub x, that's just p sub v. That's gonna be problematic because v sub y is 0, so that doesn't actually happen. Minus, so s sub y is 1, and that's just t sub. Okay, so it's just minus t sub v at constant entropy. That's equal to once again, so v sub x is just 1, and then p sub y is p sub s at constant volume. All right, that's the other relation. Yes, the other term will be 0. Check it out. I am not gonna waste my time on that. Yeah, so I'm just gonna say this is equal to minus. Cool. Amazing. Now the final relation will be when you have v and, so x equal to v and y equal to temperature. Put that in, what do you get? So p sub v doesn't make sense, it's not going to be there in any case. So you just got minus t sub x is oh wow. Okay, that's actually gone, right? So t sub v, that's actually gone. Fine. So it's got p sub y, which is p sub t at constant volume. That's equal to that's 1. So just s sub v at constant at constant temperature, I suppose. Yeah, cool. So these are the only real relations that we got. want to use. Everything else is just something that's coming from the question. Okay, cool. There's also like some relations with mu and stuff involved, but for the most part, most questions won't be asking that, so we'll not care about that. But these are the 4 most commonly used ones, so we'll keep those handy. And also there's like 2 more relations, but we won't derive them. Okay, cool. So now let's get to the question. So first we want to use an appropriate Maxwell relation to calculate partial s upon partial x at constant temperature. That's to say that we just want s sub v at t, and that is available over here. So we just calculate p sub t at v, right? And this we can certainly calculate. In this context is just j sub t at constant x value. I'll just wait a second, I'll come in a bit. Alright, let's just get back to it. So we want j sub t at constant x. How do we do that? So you're given j as a function of t and x, right? Just differentiate. So j is yeah, right, with respect to so x is constant at that point. So just get minus b plus cx. Yeah, that's what this quantity is. So use an appropriate maximum. Fine, we got it. So s sub v at constant temperature, that thing is just equal to minus b plus cx. Cool. Next question, please. Show that a. What is a? I don't know what a is. Oh, okay. Cx equal to ax part. Okay. Show that a is in fact independent of x. That is dA upon dx equal to 0. So a is just a function of x, right? Ah, that's interesting. So, okay, there's like some stuff that this implies actually. Yeah, so you know that c sub x is basically, so c sub v is basically just you know, it's just t s sub, okay, that's probably not a good idea. Whatever. So s sub t at constant volume, right? That's what this thing is. Okay, let's actually do it the organic way. So it's basically the energy's derivative with respect to temperature at constant volume. That's what c sub v is. So now what we want to show is that okay, let's actually not do that. Let's actually go with the other route. So you know the d is just tds, all that stuff. So at constant volume d is just tds, and so that just means that cv is just, you know, t times partial s upon partial temperature at constant volume. That's what cv is. Yeah, right. So s sub t at constant volume is not anywhere in our relations. That's because s and t are pairs which you cannot use essentially. Okay, but that's not our concern, because all we really want to show, okay, so first of all, this is actually equal to a of x times temperature, so this cancels. So all you're essentially saying is that s sub t at constant, well, in this case x, that's equal to, well, just a function of x basically, right? So essentially just have s, so the entropy, they just gave you the entropy, that's awesome. So that's just equal to the temperature, some function of x, and then plus some function of temperature. Cool. So you actually have the yeah, wow, that was amazing, isn't it? In fact, you can figure out what a is. This should be easy. So just to make sure, yeah, okay, I think we are having a sane argument over here, nothing too complicated. Yes, I mean, this implies that this is the case, and that implies this is the case, obviously. But now with this you can sort of do a lot of stuff, because you can use this relation, right? And actually what, yeah, so differentiate this thing with respect to the volume. Okay, it should be x over there, sorry, with respect to x, and let's just see what we get. So you just get at constant temperature, obviously. So you just get t a dash of x, and that's equal to minus b plus cx. Amazing. So you actually have a dash, oh wait, but that's involving temperature over there. Well, did we mess up somewhere to calculate this quantity at constant temperature? So what did we use, by the way? We used this thing. So the temperatures at constant x value. Yeah, sure. So using that, you should actually be able to recover this thing, right? Mm-hmm. At constant temperature, just like E dash of x. Sure, so this is supposed to be this quantity. Minus b plus c. So this is weird because what it's basically saying is that this should be. So if this function actually is non-zero, then what this implies is that. Oh, this implies something bad. This implies that you just have. Oh god, this doesn't even make sense, right? Wait, but okay, let's just rewind and do this again. So c sub v, that's just partial. So just like t partial s upon partial t at constant volume. I suppose that's the way it is. Mm-hmm. That's equal to a of x times of t. So obviously you just have this quantity. Um, yeah, okay, so add to constant x. And so integrating this, it's obvious that this should be b, obviously, sorry. We integrated with respect to temperature, this should be b of x. Yeah, okay, stupid mistake, but it makes sense. Okay. So now the derivative of this quantity will actually just be b dash of x, and that's equal to minus b plus cx. So what this suggests is that, well, a dash has to be 0. Yeah, pretty much. Because if a dash is not 0, then there's some temperature term involved at some particular x, but that should not happen. So we just have a dash of x equal to 0, and that's actually kind of what we wanted to prove in the first place. So essentially you're saying that a is just a function, and so instead of writing c is a of x times t, we could just write that, oh, cx is just at. So essentially you have all the information to recover everything that you want. That was crazy. Okay, so and you also know like b dash is just this quantity, and so we can actually get what s is from that. So we can just get s is at plus, so what is b going to be now? B dash is this quantity, so just integrate that with respect to x. So we just get minus bx plus cx square by 2. Mm-hmm. Amazing. Plus some constant, so just put that as constant d. I don't like the variable d though, so just put capital D, whatever. I suppose that's the thing. Yeah, so this is the. So B part is like done. We are pretty much done with it. C part, yeah, so given expression for s of t and x, assuming that s of 0, 0. So the general expression is just this thing. But now they have given us another constraint, that is s of 0, 0 is s naught, which is to say that this should be s naught. So we are pretty much done with that as well. All right, next we want to show okay, so calculate the heat capacity at constant tension, something like cp, basically constant pressure, heat capacity, whatever. So basically just want to calculate this quantity t partial s upon partial t at constant j, and that shouldn't be hard, right? So it's a function of t and j. Mm-hmm. Okay, at constant j, that's problematic. So what do you know? You know that j is just ax minus bt plus ctx, right? Yeah. Hey, so from that you can sort of get the value for t and then substitute that in there, and then it's gonna be doable. Okay, so let's just do that. Right. So what do you have? You just have or you can get the value of x, but whatever. X is like more problematic, so this is probably the better thing to be doing. Yeah, sure. So what do you have? Just have t times of cx minus b, that's equal to j minus ax, right? So just have t is just j minus ax upon cx minus b, and now putting that in there, you just have capital A times t. So essentially what you're saying is that, so you have s as a function of t and x, obviously, but you can also write s is equal to, so t is this quantity and that times of a, so capital A times j minus ax upon cx minus b. Now minus bx plus cx square by 2 plus s naught, all of that is there, but now you just have it as a function of j and x. And so now we can tackle d. We are saying calculate the heat capacity at constant tension, so keeping j constant, what the, as a function of t and j. Are you serious? Okay, this whole thing is problematic. We can't be doing that. So we'll have to substitute x inside of it. Okay, this isn't good. Yeah, right, we'll just have to substitute that inside. That's a problem, isn't it? Partial s by partial t at constant j. Oh, okay, okay. So first, is just figure out what ds is going to be or something. Yeah, fine. So just calculate this thing. So it's just gonna be t times this stuff. So a minus, well, just the derivative of this time, this thing, but you just have to have this, and this times the derivative of this with respect to x, which is just minus b plus plus c times of x. But well, whatever. Yeah, that's what this quantity will be. Now we'll have to figure out what this thing. Oh, so what's minus b plus cx, by the way? Yeah, we have seen that somewhere, right? And so minus b is just some constant. Well, cx is something that we have seen, I suppose. So you can substitute what x is in there, and that will solve stuff. But okay, let's not get carried away. Just wait a second. Right. Sorry, I got interrupted. Anyway, so first we just need this quantity. What's partial x by partial t at constant j? Right. So if you just figure out what dj is that's a funny name. Anyway, that's just equal to a dx minus b dt plus c x dt plus c t dx, right? So if you set this equal to 0, then that is going to give you the dx by dt term. And so collect all of this stuff. It's got a plus ct, okay, equal to b plus cx times dt over there. So just have dx upon dt is equal to, this should be minus, this should be minus, sorry, this is getting much more complicated than c. So it's b minus c. So what the hell? And I thought this was going to be better than that. There's a plus ct involved. Oof. Couldn't you have like used up that equation somehow? Yeah, apparently that was too much of a deal, huh? Not good. Certainly not good. But that's just how it is. Fine. So you want everything to be as a function of temperature, right? I just have to do this thing. Fine. So what is this? dx by dt is just b minus cx upon a plus ct. So the equation is something like t times of capital A plus so b minus cx squared upon a plus ct. Now obviously you want to fill in x, otherwise this doesn't really make sense. But yeah, this is the equation. A plus ct, yeah, a plus ct, cool. So this is essentially our value for s, not s, what was I going to say? Yeah, okay, this is the value for c sub x, in fact. Wait, right? No, c sub j. C sub j is this quantity. Cool. So as a function of t and j, right? So we want to substitute this thing as a function of t and j. Let's just get it done with. So we just have x times of a plus ct is equal to b, so j plus bt, right? That implies x is just j plus bt upon a plus ct. Amazing. Put that in there. What do you get? So just get c sub j is equal to t times of a plus this stuff. Oh god, this is horrible. Yeah, fine. So just like something a plus ct cubed, and over here you have something squared. What is that something? So you got b minus c times of x, right? Cool. So put ab plus plus bct minus c times of x, which is cj minus cbt. Oh, at least some stuff cancels out. That's a relief. So this cancels. just have AB minus CJ squared. Cool. So that's our equation. All right, next question. So the D part is also done. Next question. So the second question is, we should probably be doing it on the next page. So this is the first question. The second question. The second question is, um, a gas obeys the equation of state P times V minus NB equal to N kBT and has a heat capacity CV independent of the temperature. Fine. N is kept fine. So N is fixed throughout. At least that's a relief. So just given the equation of state, we want to find the Maxwell relation involving S sub V at constant temperature. So N is constant. Just ignore that. So S sub V at constant temperature, well, that's this obviously. So this is equal to P sub T at constant volume. I'm going to copy this actually. Yeah, so this is the relation. Cool. Now what do we do with that? Find Maxwell relation. So just figure out what this value is. P sub T at constant volume. Cool. So just differentiating this, keeping volume constant, you just have dP. In fact, it's pretty easy. dP upon dt at constant volume, that's just equal to nkb upon V minus NB. Yeah, that's the thing. So that's what S sub V. Okay, right. So this is just equal to that. And that's equal to this quantity. Cool. All right, next. So this is just the first part, right? Yeah. This is part A. Let's go to part B. Part B is, by calculating dE as a function of temperature and volume, show that E is a function of T only, in fact. Okay, cool. So we want to figure out what partial E by partial T at constant volume is and what partial E by partial V at constant temperature is. Yeah, that's the goal, isn't it? Right, so this is probably doable. What about this one? Because this is just the, what is this? It's just CV basically, right? And that you can sort of do. I think so. So I guess another way would be to calculate the entropy first, right? Calculate the entropy is most likely better, because yeah, right. Wait, but just given the equation of state, we want to show that it's only a function of temperature and N only. So function of temperature. Okay, wait a second. So what should happen is that this quantity should just be 0. So partial E by partial V at constant temperature is 0. Partial by partial V at constant temperature. Constant temperature, that's a problem, isn't it? dE as a function of T and V, that's a problem. We can figure out what dF is as a function of T and V, but this is hard. Okay, so we'll have to go to entropy, otherwise how am I even going to solve this? So you have S as a function of V and temperature. So, yeah, okay. I guess this is okay. We can use this fact to integrate this and then get something for S. So S will just be, integrate that. You just have N kb natural log of V minus NB plus some constant or whatever, but plus some function of temperature. That's the idea. All right. Cool. That does not quite help though. Anything else that you know? You know that at temperature equal to 0, this guy should just stop moving, essentially. Can we apply the third law here? Probably. So it's like, fine. So at t equal to 0, your derivative of s with respect to anything really, that should be 0. Well, this is independent of temperature, so it doesn't even make sense. That's a problem. E sub t at constant volume. Right, this is problematic, isn't it? It sure is. Am I missing some? Oh, okay, I am missing some information. So it has a heat capacity independent of the temperature. Oh, that's an important part. So the heat capacity is independent of temperature. Once again, what is Cv though? It's just it's just partial S upon partial T at constant volume, right? And you are saying this is independent of its temperature. So what we can sort of say is that okay, this is a function of volume and temperature. So the derivative of this thing with respect to temperature at constant volume, again, okay, that's gonna be 0, right? Oh, I see. So this makes sense. So you using dE as a function of temperature and volume, you can just say that, well, so dE is just partial E by partial T times dt, so at constant volume, times dt, plus partial E by partial V at constant temperature times dV. Sure. So this quantity is something that you have dealt with, right? Yeah, so this is just Cv essentially. This is Cv over there. All right. It's independent of temperature. All right, cool. But it is in fact dependent on the volume. Wait, but how does this independence of temperature give us anything nice? I don't know. Okay, what about this quantity? Partial E by partial V at constant temperature. This is not helping. V as a function of temperature and volume. Okay. At constant temperature. No, this does not make sense. Now we'll have to deal with entropy first and then we have to go to the energy, because otherwise it doesn't make sense. Cool. So you already know what S looks like, sort of. And maybe you can use that to figure out what this Cv thing should be. So yeah, so you know, like Cv is basically just T S sub T at constant volume, right? And so you are saying that this quantity does not depend on the temperature. It's independent of temperature. So it does depend on the volume though, right? So this is just a function of uh, the volume. Okay, cool. Oh, wait, so you have this, right? What you can say is that entropy is just, so once again, just nkb natural log of v minus nb plus some function of temperature, right? So then you can take s sub t with this at constant volume, and what you'll just get is this, that just have right, so just nkb natural log of all of that. Also all of that is just something that's related to volume, that's constant, so that's not important. So it's got f dash of t basically, right? So just have t f dash of t. This quantity is supposed to be independent of temperature. What does that mean? Well, this has to be some sort of a constant, right? Yeah, because this is certainly a function of only the temperature, and it's also independent of that, so it's a constant. Well, that just implies that f is something like f dash of t. So yeah, right, f is just the integration of c upon t, right? So it's something like c natural log of t or something like that. Cool. So just have some constant and the natural log of t involved. That's a massive progress actually, because now we have the full relation. So plus some constant, and that constant is obviously a function of n and all that stuff, and then natural log of the temperature. Cool. And so you can combine, so this constant is proportional to n most likely because of extensivity, and so from that you can sort of say that this has to happen. So t power some quantity, we don't know what that quantity is, but let's just call that quantity as, I don't know, c. Yeah, that's good. And so now you have actually a better equation for the entropy. Okay, so now that we know what the entropy is, probably it's going to be easy to figure out what the energy is, right? Okay, actually there's another thing that we could be using. So before doing that, let's do C. So show that gamma is Cp by Cv, that's equal to 1 plus n kb upon Cv. So it's independent of temperature and volume. Okay, cool. Let's just do this thing. So you know that Cv is, once again, just so now what's Cv then? Partial S upon partial T at constant volume. Okay, and Cp is at constant pressure. Fine, shouldn't be that hard. So this is just n kb upon this whole stuff, v minus np t power c. Right, just think. It's actually plus some sort of a constant, but we kind of don't care about that stuff at this point. Okay, so n kb upon v minus, that stuff, fine, times the derivative of this with respect to temperature. Okay, wait a second, so that v stuff, okay, that's going to be cancelled in any case because the volume is constant. So basically just have n kb's times c is some constant, and yeah, right, so it should just be n kbc, and then the natural log of t derivative, so just 1 upon t over there. Is that constant volume, right? Okay, cool. What about cp? Cp is at constant pressure. Nice. So how am I gonna do that though? So you can once again just split it apart. So now just have n kb c upon t, but plus you also have this stuff. So n kb. Oh wait, actually we can just directly use this fact that v minus nb is just n kb t. Just n kb t upon pressure. So you can just use that fact, and then this whole thing can be written as natural log of p power minus 1 t power c plus 1, and some other constant, and then you have n kb over there, and then some constant stuff, whatever, doesn't really matter. And so instead of this, you would just have c plus 1 over there. That's the only difference. Wow. Okay, that was easy. Yeah, right. So that's the thing, huh? So you have Cv, and you also have Cp, and from here it's actually very easy to show that C holds true, as in Cp upon Cv, that's just equal to n, so 1 plus n kb upon t or something. Wait, why is that 1 plus n kb upon Cv? What? Okay, n kb upon t, and then okay, let's just see what's going on. Am I messed up? Oh, okay, yeah, right. So this should be that times the temperature. So okay, right, this is the correct equation. Sorry for that. It's always temperature times something, right? So thing. And now it's easy. It's very easy to see what's going on. So C is just some constant. We don't care. And so what you have is that Cp is just equal to Cv plus nkb essentially. And so obviously Cp upon Cv is just 1 plus nkb upon Cv. And so yeah, this is easy. And so you're seeing this is a function which is independent of temperature and volume, obviously. Yeah. Alright, so that was doable, I suppose. But this was actually part C and not part B. Let's go to B now. Okay, actually let's go to part D instead. Right, so we actually want to write energy is a function of pressure and volume, because yeah, I guess so. Wait, actually you could also write dE as a function of, right, so now at this point we are at a stage where we can actually do this thing. So let's actually tackle the question B. So you want to write dE as a function of temperature and volume. So you know that dE is just, well, TdS minus PdV at this point. But ds is something that you can calculate because you have this equation. Amazing. Yeah, right. This should be doable. So P you already know, and dV is over there. Yeah, whatever. So P as a function of volume and temperature, you know, and so you can just write that as so you know nkBT upon V minus NB, and that times of dV, right? And you also know what ds is, so just t times of that stuff. So ds will just be, actually just write that down. So ds is what, nkb, and that times of this stuff, it's gone, okay. So it's just dv upon V minus NB, and plus some constant c times well dt upon, yeah, dt upon t. That's pretty much the thing. That's what ds is. So this times of the temperature, right? So you'll just have TdS is just equal to nkb TdV upon V minus NB. What the, okay, fine, whatever, plus CDT. Amazing. And so this minus of this stuff now, look at this stuff, this is exactly just that, so it cancels. So what do you have? You just have that dE is exactly just nkb CDT, and that implies that, oh, the energy does not depend on the volume somehow. So yeah, you just have the equation apparently, which says that energy is just a function of temperature. Nice. So apparently it's sort of like the ideal gas, but not quite. So that E is a function of temperature and N only. Yeah, it is. Alright, cool. And this just implies that energy, well, that's just nkbc times T plus some constant. Amazing. Next question. Okay, actually D. By writing an expression for E as a function of pressure and volume, or otherwise show that the adiabatic change satisfies this relation. PV power. Okay, cool. You don't even have to do this thing, because if it's an adiabatic thing, then what is happening is that the entropy is not changing because there's no heat input. But that implies that this quantity has to be constant. So just have V minus N P T power C is constant, right? Cool. Yeah, okay, kind of remember what gamma is. Gamma is just C plus 1 upon C, by the way, right? Yeah, cool. So now you can use that fact, because look, V minus NB, sorry, okay, this T actually, right? So that T can be written as, so just P times V minus NB upon K. Okay, fine. So we just get V minus NB to the power of C plus 1 and then P power C. That's actually equal to constant, right? And that implies that P times V minus NB to the power of, right? So this is actually very easy to see. So D part is done. Okay, next question, third. Question 3 is, many metals become superconductors at low temperature T and magnetic field B. The heat capacity of the two phases at zero magnetic field are approximately given by this and that. So the superconducting phase and the normal phase. Fine. Where, so this is like with respect C sub S, C sub N. Okay, these subscripts mean superconducting and normal. So the heat capacity is at constant volume, obviously. V is the volume, okay, whatever. There is no appreciable change in volume in the transition, and mechanical work can be ignored throughout the process. Cool. Okay, that's a big question. It's a lot of text. Fine, so we want to calculate the entropies of the two phases at zero field using the third law of thermodynamics. Oof. Thought so. Fine, so the superconducting phase and the normal phase. Are you serious? Like, you haven't given us the transition, have you? Comes superconductors at low temperature and magnetic field. The magnetic field, how am I supposed to use that now? Of the two phases at zero magnetic field. Ah, right. So the magnetic field is actually just not being used apparently. So it's just dependent on the volume and the temperature. Cool. And that's the heat capacity. So if I graph these, so the first is like V alpha T cubed. So it's something like that. And then this is slightly different. It's like V times T, and then you got beta T squared plus gamma or something. So yeah, it's also starting off at this, but then it doesn't increase that fast, so it's gonna meet it at some point. Okay, so this is what's gonna happen in the normal phase. Apparently in the superconducting phase, this will be the thing. Yeah, I mean, yeah, because this is the only point where these are gonna meet. So yeah, right, this makes sense. So I'm assuming that these are positive constants. I actually don't know, but whatever. Yeah, there is no appreciable change in the volume at this transition. Mechanical work can be ignored. Fine. Calculate the entropies of the two phases at zero field. Okay. Using the third law of thermodynamics. So we'll have to figure out what the temperature is where these two become equal. And that's to say that, oh wait, okay, you have beta t power 3. That's weird. But essentially what you have is like alpha t square is equal to beta t square plus gamma. Let's just have t square is equal to square root of gamma upon alpha minus beta. This is where you have something changing. So like whatever is the entropy at that particular point. Actually no, this was a graph for what it was a graph for the specific heat at constant volume, right? So now I just know that after this is gonna be a normal conduction, but before that it's a superconductor, right? Yeah. So what I need to do is figure out the entropy at this particular point, right? So for the entropy at the zero, the t equal to 0 case, we'll have to look at what happens at the low temperatures. So that's when it becomes a superconductor. So we basically just have this, that the heat capacity is, for our concerns, is just alpha Vt cubed. I think I've seen something similar before, I don't quite remember, but anyway. So from here what we want to do is figure out the entropy. Cool. So this is obviously just T partial S upon partial temperature constant volume, that's equal to alpha Vt cube. So what this implies is that it's just alpha T square, right? And so using this we can just say that S is alpha V upon 3T cubed plus some function of the volume, right? But then you know that the derivative of entropy with any other variable other than temperature at t equal to 0, that should be 0. So what that implies is that this is basically a constant. You just have plus s naught, and for our case we'll just assume that that is actually 0. So yeah, just have this quantity s is alpha v t cube upon 3. Nice. Right, I guess that makes sense. So you actually have the entropy now, for at least the superconducting phase. Okay, let's also figure out the entropy change. Yeah, for the other case, right? Okay. So for the other guy, just have once again partial s upon partial t at constant volume, that's just equal to v times gamma plus beta t square. All right, so I just want to be integrating this into temperature. So just get entropy is v times of gamma t plus 1/3 beta t cubed plus some function of v, right? Now can you pretty much say the same thing as before? I don't quite know. So you know that at temperature equal to this quantity, both of these functions should become identical, right? Yeah. So okay, put that as the case, right? Just put temperature as gamma upon square root of alpha, so square root of gamma upon alpha minus beta. So we'll just have uh, over here you just have some constant, but what is that constant? Just v times, sorry, volume times some constant. So just gamma power 3 by 2 upon yeah, this is concerning actually. So what do you actually have? Just have f of v is, so just call this thing as t critical. I don't know, just giving us some random name. So what do you have? Just have volume times this stuff. It's just gamma t plus 1/3 beta t cubed minus 1/3 alpha t cubed, right? Which is just volume temperature critical, obviously. So the critical case is just that gamma plus 1/3 beta minus alpha t square. What's t? So t critical square, well that's just equal to this quantity, so it's just gamma upon alpha minus beta. Ah, that's okay. So you somehow figured out the critical everything. Okay, wait, so fv is independent of the temperature, right? Ah, okay, it makes sense completely at this point. So just using continuity you can get this done, right? So this is just what v square root of gamma upon alpha minus beta times gamma minus, guess what, 1/3 gamma. It's just 2/3 gamma over there. And so now you actually have what this f of v should be, and so it's just this quantity. So it's just volume times this whole bizarre thing. So gamma square root of gamma upon square root of alpha minus beta, right? So that's your entropy for the other case. Amazing. So now you have your two equations. So that's like part A, I think. Yes. So part A is done. What's part B? Part B is, and notice that these equations are like solid because you can actually calculate everything. Experiments indicate that there is no latent heat of for the transition between the normal and conducting phase at zero field. Use this information to obtain the transition temperature as a function of alpha, beta, and gamma. Wait, didn't we actually just do that? I think so. Yeah, right. Oh, okay, yeah, we actually directly use that. Ah, should have known. Right. There's a problem. I get it. So it could be that, so the specific heat goes like this. Initially, it just goes cubically and then it goes quadratically. And we sort of assume that at this point where these two specific heats are equal, you're going to convert from superconducting region to the other region, right? But what if you were able to convert over here, like happens in case of ice and water, right? You convert where your specific heat for ice is like 0.5, for this is 1, but you still convert. So it should have been possible. Okay, so the thing is that there is no latent heat, and that's what allows us to do this transition, because then that implies for changing the temperature by a dt amount you don't have to put in heat, and that can only happen if the heats, so the specific heats are equal. And so that implies that yeah, this has to be the same value, right? And that's how we get that temperature thing. So we already have the critical temperature. Oh, so they actually called it TC as well. I didn't think that would be the case. Anyway, next thing. At zero temperature, the electrons in the superconductor form bound Cooper pairs. As a result, the internal energy of the superconductor is reduced by an amount V delta. V delta. I don't get it. What happened? Electrons in superconductor forms, whatever, some effect happens. So as a result, the internal energy is reduced by an amount V delta, i.e. the energy at the normal phase at equal to 0 is what? No, this doesn't make sense. For the metal in the superconductor, respectively, calculate the energy of the metal. Ah, okay, okay, this is hurting my brain. So in the last question, we assumed that for the second case, it will have to first become a superconductor and then go to below temperatures, right? It doesn't make sense for it to just reach T equal to 0 with the normal equations, right? So how come you can do that for energy? Like, what the? No, this doesn't even make sense. Wait, so in that case, we should have probably used that fact that, well, this will. Okay, so apply the third law for the normal phase as well. That doesn't even make sense. Why would I do that? If we know for sure it will never reach T equal to 0. Right? God. Okay, so that's implying that this quantity is supposed to be not there in the first place. That's some discontinuity between the things. So there's like, no, but this should be a reversible transition then, and there's no latent heat. How does that make sense? There is no latent heat. This is a reversible transition. There's a work energy theorem, well, that says that the amount of heat that transferred. Yeah, okay. I understand that. So I apply the work energy theorem and it all makes sense. But in case of the entropy, the entropy of the whole universe does not increase, right? The heat lost by that should just be equal to the heat gained. If there's no heat input inside, how is that even making sense? No, this is wrong. How come the entropy is different? Because if it's different, then there should be heat input. But if there's a heat input, then that implies latent heat can't be 0. None of it makes sense. Entropies must be identically the same at that transition point. Right. What about the heat capacities though? Could they be different? Sure, I guess. But then the work energy theorem doesn't hold, right? Because you know that to change the... Oh, okay, you don't use the work energy... Right, sorry. The heat capacities do not matter because you're not changing temperature. You talk about latent heat. So this whole thing is wrong. Sorry, this is not making sense, right? Yeah. What we should have done is actually just equate the entropies, right? Or more like entropy upon volume, but whatever. So then you would have got the correct equation. So you would have got alpha T sub c squared is equal to 3 times, yeah, right, that's the thing, 3 gamma T sub c. Okay, actually that's gone, so just plus beta T sub c squared. And so you just have got T sub c is equal to square root of 3 gamma upon alpha minus beta and not square root of gamma upon alpha minus beta. This is the correct thing actually. Right, sorry. C is okay, now this makes a bit of sense, but it's still weird. I don't know. Zero temperature the electrons, fine, whatever. So just given energy is E naught and E naught minus V delta for the metal and superconductor. Calculate the internal energies of both phases at finite temperature. Cool. Shouldn't be too hard to do. So let's just figure out the thing. So you can just have dE is equal to TdS minus VdV, right? Yeah. So since the volume does not change, you just have this equation essentially. So integrating that is like integrating TdS. So TdS, so energy at some temperature T is just the energy at 0 temperature plus this integration from T equal to 0 to, well, some temperature T. So let's just do it for the normal case. So just have E sub n is E naught plus integration T. Well, what's ds now? Because this is your entropy, right? So just have alpha v t square dt, right? So this is just E naught plus alpha v t power 4 by 4. Yeah, that's the thing. All right, let's also figure out the thing for the other guy. So E sub s, I think I just did it for E sub s. Yeah, sorry, this was E sub s, this is E sub n. Yeah, right. So E sub n is integrate the derivative of this quantity. So it's E naught minus V delta plus integrate this guy. Yeah. So this is just V times gamma delta. So sorry, gamma T plus, that's gonna cancel out and all that stuff. Cool. So just B T power 4 upon 4. Right, that's the thing. Cool. All right. So by comparing the Gibbs, calculate the internal energies of both. Fine, did that. By comparing the Gibbs energy in the two phases, obtain the expression for the gap in terms of alpha, beta and delta. All right. So you know that at a critical temperature, well, there's like transition going on. Yes, the latent heat is 0. That implies that the change in entropy, that's supposed to be reversible. So like it does it automatically without any heat input. Cool. Also, what should happen in that case is that the energetics should also work out, as in, yeah, the energy for, or more like the energy in the, what am I going to say is like, okay, what was I going to say? Right, the energy of the normal state and of the superconducting state during the transition, those should be equal, I suppose, right? Does this make sense? Like it's valid? I think so. Right, okay, the Gibbs energy should be the same apparently. Right, okay, that makes more sense, I think so. Wait, so you just have G equal to E minus Ts, but you know that the entropies are in fact the same, so that kind of implies that the energies are same. Oh, so we can just like equate the energies and that will give us the V delta. This was easy. Yeah, so just have V delta is equal to, just subtract these off. So just have this was easy. It's just V times gamma T plus beta minus alpha T power 4 upon V. Cool. Actually it's just supposed to be TC, but like whatever. Yeah, right. So you just have delta basically. Cool. So you just put that in there. Just have gamma TC. There's a T power 4 term involved. There should there be T power 4 term involved though? Oh, this should be T squared by 2. Sorry for that. Yeah, okay, that makes more sense. So you just have gamma upon 2. So gamma upon 2, and then Tc squared, which is just this quantity, so just 3 gamma upon alpha minus beta plus beta minus alpha squared, which is identical to alpha minus beta squared. So like, it's not squared, that's the 2 from there. So just beta minus alpha, and then this quantity. So it's like 9 gamma square upon alpha minus beta square. Yeah, okay, that's the way it is. That's what our delta will be. And what's that equal to? is just, so it's a minus over there, so it's just gamma square upon alpha minus beta times 3 by 2 minus 9 by 4, right, by 4. It's supposed to be there. Yeah, that's the way it is. So what is that now? It's like 6 by 4. Okay, then how is that negative? Oh, it should be 16 because you squared that. So this should be 16, I suppose. No, wait, what? Something is messed up, isn't it? 3 gamma upon. Okay. How does that even make sense? 3 by 2, and that's, wow. No, it doesn't make sense. If you had an extra t and that's how you got this. Yeah, that's about right. And subtracted that. And you should be having a beta minus alpha. Yes, that's how it is. So that gives you negative. Sure, it does. So it's 9 upon 4. How does that even make sense? It's bigger than 2 times that. That should not be the case. You have TC power 4 for some reason. Are we sure we got the TC thing correctly? Square of that, and that's 1/3. It's beta minus alpha. Yeah, that looks about right. What's so problematic? Why am I getting this thing? E sub n is... Oh, sorry, I switched this up, didn't I? Sorry. So this should be minus v delta, and this should just be E naught. Right, okay, that explains a lot. So it's actually negative delta that we are calculating. That makes sense. So negative delta is just this quantity, which is like minus gamma square upon minus beta times 9 by 4 minus 3 by 2, whatever, which is like what? 6 by 4 minus this thing is just minus 3 by 4, so that's just 3/4 of that. So essentially just have delta is 3/4 of gamma square upon alpha minus beta. Yep, that's the thing. Okay, that's good. Not negative delta, just positive delta. Alright, D is done. E is in the presence of magnetic field B, inclusion of magnetic work results in dE is equal to blah 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 whatever, where M is magnetization. The superconducting phase is a perfect diamag. Okay, so why is there a mu n? Okay, whatever. Expelling the magnetic field from its interior such that ms is equal to minus vb upon 4 pi in the diamagnet. Expelling the magnetic field. Wait, sorry. Inappropriate. The normal metal can be regarded as approximately non-magnetic with M equal to conjunction. The previous result to show that the superconducting phase becomes normal for magnetic fields greater than this, given expression for B naught. So they have given us dE as a function of so I don't think we are going to change n really. The superconducting phase becomes normal for magnetic fields larger than that at some particular temperature, right? Okay, so we want to figure out the phase transition, and okay, cool, I get it. So all of this is just for the the entropy and all that stuff is just really for the case when you have I was going to say zero magnetic field, right? But now it's different. So now you have this extra thing, TDS plus all that stuff. So Perfect diamagnet expelling the magnetic field from its interior. Wait, what? Perfect diamagnet expelling the magnetic field from its interior. But that's to say that the entropy remains the same, because if the interior does not change, there's no changing in the arrangement. So the entropy is still the same. Oh, that's nice. Is that the okay? Cool, but the energy does change. Fine. What is Mn? It's like magnetic field, and then you have this capital M thing. It's the magnetization. Okay, they have given us magnetization, the functions for them basically. Minus Vb upon 4 pi. It's for the superconducting region. Cool. So we know the critical temperature when the transition takes place at temperature equal to 0, but in fact even now it's going to be the same, because well, latent heat is still 0, right? Yeah, but the energetics are now not the same anymore. So we'll have to figure out what the G thing is, right? Gibbs energy now. Wait, so TC is already calculated apparently. Uh, so now what we want is that a particular temperature, what is the magnetic field such that that happens. Fine. Just think about it. Oh, right. So we'll have to equate the G values. So you already have the entropies. So we're at some particular temperature. Cool. The energies, you also have them, in fact. So you have this delta. Yeah, right. So I guess it's time that we plug everything in and just, compute it. Yeah. So this is just at constant what? So it's at magnetic field equal to 0, right? Okay. So now you have to increase the magnetic field, and that causes this to change. Yeah, okay, sounds about right. So you just have to add an extra term. So you just have to add the term. So in case of the superconductor, it's just the minus Vb upon 4 pi and all that stuff. So it's like minus V upon 4 pi Pdp. You integrate that. So it's just minus V upon 8 pi B square. Right, yeah. That looks about right. In this case, it's just 0. So wow, that's not there. Right. Cool. Now let's do this thing. So what's the Gibbs energy for the superconducting phase? That's just, so delta you already know, it's just this quantity. I am quite tempted to put that in there actually. Yeah, right. So let's just actually do that. It's just E naught minus V delta plus this whole bizarre thing. So V times of alpha t power 4 by 4 minus B square upon 8 pi. Right. That's our E. Now minus TS plus PV, right? The PV thing is 0 in any case. It doesn't really matter. Or does it? Well, let's assume the pressure doesn't really matter. So this plus, so minus, sorry, TS, I suppose. So T times of S. S you already know for the superconducting phase. This is for normal phase. Just put that in there. So just V times of alpha T power 4 upon 3. Okay, and that just converts this whole thing. So now it's minus something upon 12. Amazing. What about the Gibbs energy of the normal case? So you just have this thing, E and all that. Just got E naught minus V delta plus this whole stuff minus the entropy. So T times the entropy basically. 4. Okay, you're gonna get the same stuff. So just V gamma T square by 2 plus, so I'm just gonna put the big one before that, Pt power 4 upon 12. Right? Okay, that's negative of that, so negative of this thing. Okay, and plus gamma t square by 2. Oh, but you also have that thing, so it's actually also negative. So it's minus gamma t square by 2 in fact. And then the plus v delta thing, I suppose. So just plus this whole quantity. This is actually written as negative better. And then minus basically. And then delta. So delta is just this quantity. 3 gamma square upon 4 alpha minus beta. Amazing. So that's this is like what we have to equate. So basically what we get is, right, I'm just gonna move this to the next page. So equate these two, and what you get is that b square upon 8 pi is equal to gamma t square upon 2 minus alpha minus beta t power 4 upon 12 minus 3 gamma square upon 4 times of alpha minus beta. So at a given temperature, this is what's going to happen. This is a beta critical, it just seems. Oh, so we also actually have to give the expression for b naught in this stuff. Okay, cool. It's minus t square upon tc squared, huh? Wait, what? How does that even make any sense? So the critical is just that. Sure. This isn't the equation that we have. B naught. What the hell? It's t squared over there. How does that even make sense? Dc square. I'm just gonna take that gamma square out. Isn't that right? Okay, the head hurts. Parts of it aren't making sense now. Dc squared. What the hell? 1 minus y the... Okay. Did I do something wrong over here? No, I did not. Yeah, I certainly did not. So then why is this happening? That's a delta term involved in there. Sure. We just equated the Gibbs energy, right? Yeah, that's just what we did. And that's how we got this B subcritical. And how is this happening? This is certainly not t square upon tc square. Expression for B. This isn't the equation that we are getting. Certainly not. Where did we go wrong? I don't think we actually even went wrong in the first place. This volume b square by 8 pi. Yeah, that's the scenario. Mu dn. But n is not changing, so don't have to worry about that. Yeah, sure, you just have the Gibbs energy. What's the big deal? Plus v delta. Yeah, sure. Just equate these two. And that should give you the equation, but it's not giving us the equation. Why? Why is it not giving the equation that we need? T critical squared, huh? So it's a polynomial in t square and all. Not a good thing. T critical squared. Nope, I don't have any idea what's going on. Gamma t square, what is this stuff? Everything's about a 4. This is... Oh, because it's a square. Oh, obviously. Sorry for that. We should complete the square first. Ah, obviously. Right. So complete the square and then see what happens. So just multiply this whole thing by, I suppose, 12. And so what you will get is... Yeah, I guess 12 is a good idea. So maybe just 4. Nah, 12 is good. So multiply by 12. You just get 3 by 2 pi b squared critical. That's equal to 6 gamma t square minus I'm still sort of not very much sold on the idea because it's having negative terms. Well, we'll see what happens. This should be a square, right? It should be, but then why is this negative? What if that was actually negative? Energy of the superconducting phase is just... Hey, why is this negative? It should be positive. Sorry for that. This should just be positive. So you have a negative involved in there. Amazing. So when you convert this, it should be negative or then positive there. Now it makes sense, right? That's just 9 gamma square upon alpha minus beta. Okay, now it makes perfect sense. Cool. As a matter of fact, take that alpha minus beta away as well. So just have 3 alpha minus beta upon 2 pi beta critical not beta, sorry, magnetic field critical square. That's equal to this quantity. So just 9 gamma square minus 6 gamma alpha minus beta t squared plus alpha minus beta squared t power 4. And guess what? This thing is just equal to 3 gamma minus alpha minus beta temperature squared. Okay, now it makes perfect sense. So just have beta critical, that's just equal to square root of 2 pi upon 3 times of alpha minus beta, this quantity, times 3 gamma minus alpha minus beta temperature. And so now we can just take away something, particularly the 3 gamma from there, and that's gonna give you what we want. Yeah, okay, it's actually square over there, sorry. Right. Yeah, so just take that 3 gamma away and then you just get this. So this times of 3 gamma and that times of 1 minus this stuff. Yeah, that's the thing. So we just have b naught, that's equal to, so just put that inside, just have square root of 6 pi gamma square upon alpha minus beta. Amazing. This is the equation. Just cut that. And so this is the equation. We don't need all of this. Amazing. Next question. Actually, we're running out of time in any case, so I guess we should stop. So yeah, in 1 hour, I think 3 questions. That's a good record because in the exam we were given 1 hour and 2 questions. So I think I'm doing good so far. Nothing too complicated. Or maybe these questions were just too easy. Who knows? Could be. But I guess we should just push on. Who knows? There are 8 questions, right? Yeah. Let's just push on. Or you know what? Okay, let me just take a break and then we'll continue. So I'll see you guys in the next video. Bye.